Paul Osmo tells me I've used the same title for this talk as I used for a paper I wrote a long time ago, which for me was the beginning of this enterprise. And how I got involved in essentially igneous petrology is best explained by the first slide, perhaps. Yes. Do I have a stick or something to point with?
Yeah.
Right. Oh, hooray, a bamboo. Goody. This is a plot which is more recent than the one that was available when I started work, because it actually contains hafnium isotopes as well. But this here is the neodymium isotopic ratio. This is what we believe to be the bulk Earth, at least what we used to believe was the bulk Earth. If you believe the latest neodymium results, that shifts it up this way. It doesn't help to understand how this comes about. And what struck me a long time ago, and this originally started with some work that Paul Gast did, is that this is extremely difficult to understand how this set of isotopic ratios, which are measured in ocean islands, comes about. And the problem is there's a lot of problems with this. First of all, this is where Moore plots mid-ocean ridge basalts. So why do the ocean islands have such variable isotopic ratios? And the sort of time scale involved in producing this evolution is 1 or 2 gigayears. But the mantle is vigorously convecting. So how in the world do you preserve within a vigorously convecting mantle these regions from which you're going to extract the ocean islands? And the ocean islands are not small. Right? You've got to have a large volume of material with a different isotopic ratio in order to actually produce this sort of behavior. And Paul originally found this in lead isotopes, but none of these are lead isotopes. There's a good reason for not using lead isotopes for such plots, because of the difficulty of actually calculating what the fractionation of lead and uranium are in a melting system. So that's one problem. The other problem is how in the world do you extract, if the system is convecting vigorously, right, and here is a set of numerical solutions for vigorous convection, and the bottom one here, if it's just upper mantle convection, and I don't really want to get into whether it's upper mantle or whole mantle convection, this stirring that's produced here only takes around about 100 million years. So this is too short a time to accumulate the isotopic anomalies which we're seeing. And then how in the world, from such a system, which started off with just a box here, and you can see what it's got drawn out into, there's dots from here all over this region, and this is just 2-dimensional convection. It's even worse in 3-dimensional convection. How in the world do you actually extract from these things, from this sort of stirred business, enough material to make an ocean island? And that was clearly, the whole enterprise had some bearing on mantle convection, and furthermore on the history of mantle convection. And so I, rather naively, being brought up as a physicist rather than as a petrologist or geochemist, thought all I had to do to find out how you extract melt from the mantle, which clearly is a crucial part of this, was to go and look at the igneous petrology textbooks, which I did, and found essentially nothing except a notion of filter pressing. And filter pressing is really completely a laboratory-based enterprise. You put something which contains water like a sponge between two filters and press it, and out comes the water. Well, how in the world they thought this actually applied to the mantle, I have never understood, and I've not got any closer to it. The other problem was that the igneous petrologists believed you needed more than 5% melt before you could extract it. And another thing which I looked and looked and looked for what the reason for this belief was, and finally discovered the reason was that they couldn't actually see less than 5% melt in their charges in the laboratory, that there was no physical foundation for it at all that I could discover. So I thought, well, all right, I'm trained as a physicist, I know some fluid dynamics, why don't I actually see whether somebody has got the governing equations for this separation? Now I couldn't find any. And that was really the spur for me to get involved in this. But I'm not going to talk really about that at all here, because in fact most of this meeting is concerned with the fluid dynamics, and I'm not an applied mathematician. I'm not a mathematician of any sort. I'm really a physicist, and what I want to do is to go back to the observations which have changed very considerably since the work that I did originally, and to look at what any mathematical understanding of this process has to actually take account of. And I want to do some modeling, right? And what I'm going to use is partition coefficients. When Keith and Arns and I first tried to model these things in 1991, we took, Keith produced some partition coefficients, and those are plotted here, right? Both, and the ones that matter are for kind of pyroxene and garnet. And this curve is a curve based on Wood and Blundy's enterprises. You can see we did really quite well. There are one or two bits which don't quite fit. And garnet is slightly different. So what I now do is I actually force these partition coefficients to agree with those of with Wood and Blundy's notions, and that makes some difference. You can see here this is a melt from northern Tibet. I just picked it out because it's one of the more complicated ones to model, and you can see that we now do really a rather good job on the rare earths, which is mostly what we use. And the reason why I use rare earths is actually clear from this picture. You can see that the garnet partition coefficients vary by about 4 orders of magnitude for the rare earths. So they've been designed for people like me who are not really interested in the chemistry. They want something which will tell them the answer, right? And the rare earths are ideal. They all have a valency of 3, and they behave very sensibly. They're simply controlled by their ionic radii. And you can see that we do a pretty good job now, even with some of the more incompatible elements. I'm not going to talk about this story. This story really involves depletion and then re-enrichment, and that's not, I've not yet found any ocean island which requires depletion before it gets enriched, rather surprisingly. This is now a recent, the technologies change enormously, the measurement technologies change enormously, and Jenner and O'Neill made these measurements on small pieces of glass, right, by a method which actually only destroys a very small little bit of it. And what you can see here is that this is the melting model, right, which got by inversion of that, and you can see that before I correct for fractionation, it makes 6 kilometers of melt. If I correct for fractionation, it makes about 9. Whether the elemental concentrations I've used are slightly too high, or whether this global data set actually includes some regions which are affected by plumes, I'm not sure. But you can see that things have really not changed very much from the work that I did with Bob White, who's sitting here, and Keith and Arns. The fit is still really quite good. But the incompatible elements, you can see here, and the reason why they haven't got error bars is that the error bars are actually larger than the concentrations. So these things are extraordinarily variable, even on what these people thought were mid-ocean ridge basalts. But on the other hand, the fit now to the more compatible elements is really very good. So this is essentially the basis, right, of what we've got to understand, is that these, on mid-ocean ridges, right, you get something which makes altogether sense, right, but which produces this enormous variation. Right. Now, I got fed up with, this is simply, if you take the variation here, right, this is relative to what we think is the Morb source, right, so this is a real fractionation relative to the source, and you can see that there is a very small fractionation for the neodymium and samarium. If you turn that then into the evolution, this is how far you would go in 2 gigayears. And you can see you've gone about to here. Right? So there's a great deal of stuff which is not explicable in terms of the aging of a Morb source, in terms of the mid-ocean ridge basalts. The fractionation has to be a lot bigger than you get in Morb. And I have never understood why the geochemists are so fixed on the notion that you can account for this behavior in terms of remelting mid-ocean ridge basalts. You can't. You must, the source that you're seeing here must involve more fractionation than that. Now, what I then got involved in was that I got absolutely fed up with the geochemists saying that what you should do is to measure all the elemental and isotopic concentrations in one sample, and then not doing so. They are, of all the groups I've worked with, and it's now quite a lot of people, right, marine geologists, seismologists, and people like that, they are least good at sharing their samples. So it's quite easy to get into an aeroplane and go and collect some more, which they do. They are very bad at field mapping. Right? They're also very bad at actually giving the locations. When you actually have enough locations as we do in Northern Iceland, you can tell whether they've actually recorded the GPS locations correctly. And no, they haven't. And this makes it almost impossible to work with the use. It's slightly improved now, but it has been really, when I started this, which was about 1990, it was impossible to work with the data from the literature. And I said, to hell with this, stop complaining, Dan, get off your backside and organize a program to go and collect the data and then distribute it to anyone who wants to work on it. And this is what I did, and it's had a major impact on our knowledge, particularly of the region around Thessaloniki. My original plan was to work here, was to work, have one graduate student who worked here and work my way down to here, right? In fact, exactly the opposite happened. First graduate student mapped Thessaloniki, the next, who's John McClellan, who's here somewhere, I suspect, yes, then really worked on a single flow, and increasingly what we now do is work on a single hand sample, and I'll come back to that in a minute, right, of looking at the melt inclusions in olivine. I hadn't really taken on board, right, the difference between doing seismology and doing geochemistry when the diffusion rates are so low, right, so the variability of these things is enormous. So let me say a little bit about about North Iceland. First of all, you can easily date things. This flow is from Krabla. This is a recent one. It was from the 1980s. This, when the eruption forms things like this, it happens underneath the ice. So you can tell, really, just by looking at the landscape, what the age of these are as to whether they were produced underneath the ice and then the ice melted. And 10,000 years ago, if they come out on this part, then they're younger than 10,000 years. So you don't have to do any fancy dating, which actually would be quite hard. The correlation, and this I don't expect you to take on board all this, right? This is simply a correlation between isotopes here and elements. And all I want you to take away with from here is, first of all, that the isotopes correlate beautifully with each other. This is a principal component of the isotopes. You just look down there, down to this level, you can see all the isotopes correlate with each other at a very high degree, and they also correlate with the incompatible elements. Right? And Al Hoffman complains that this is one of the few places in the world where essentially everything correlates with everything. Right? But it does make life simpler. It was actually pure luck, right, that we started to work in such a simple area. There was no, we did not have an understanding of that. But this makes all kinds of things more straightforward. And in particular, you can use this correlation, right, to actually estimate what the source region, right, which is producing this isotopic variability, looks like. And the way in which that works is actually quite simple. First of all, here's the correlation, and this is just simply the gradient. Forget all these are just simple examples of it. You can see here the correlation of lanthanum with the principal component. It's the same thing. These are the gradients of these lines, right? And you can see that as with the very incompatible ones, the gradient is very steep. It comes down, and it becomes lower, right, with the more compatible rare earths. Now you can use this, right, to actually work out what the source is like. And this I need to explain a little bit carefully, because on this depends a lot of what I'm now going to talk about. First of all, this is a plot. It's a three-dimensional plot of lanthanum versus lutetium, and in this way is the strontium isotope. Doesn't matter what isotope you use, especially in Thesteric here. But when you make the melt here, this is the initial composition. Right? It all will have the same isotopic ratio, at least the variations will be quite small, right? But there will be a considerable fractionation typically between lanthanum, right, and lutetium. Then what happens is that as the thing ages, depending on the amount of rubidium which goes into here, so the greater the concentrations of the incompatible elements, so the faster will be the evolution of the strontium isotope. So this, which is initially a line in the plane parallel to lanthanum lutetium, will evolve out of that plane, right, because the strontium isotope the ratio will increase. And here it is after some time. So by looking at the correlation between the isotopic ratios and the elemental ratios, which are these lines, this line and this line, you can then see what is the lanthanum lutetium ratio in the source which is producing this evolution. And because of the correlation being so good in Thesteric here, which was the first place we tried this, the enterprise comes out quite cleanly. And here, this is, on this plot, this is the observed, on all these cases, this is the observed ratio of the concentration to the isotopic ratio, and this is the calculated one for various different models. So if the fractionation is produced, for instance, by extracting a very small amount of melt from garnet peridotite, this is the slope that you'd expect here. This is the slope that you observe. If they agree, the slope should be 1. Well, it isn't. The fractionation is not as great as this source. On the other hand, here's our Morb source, which I told you really didn't work in terms of aging, and you can see that no, the fractionation is much greater, observed fractionation much greater than that you'd expect for more melting. This is from an ocean on Java plateau. We're getting closer. You can see that in all cases the behavior follows the incompatibility. Right? It isn't a random pattern. But if you melt plagioclase peridotite, you get a completely different pattern, because things like strontium, for instance, are compatible, right? And then you get a scatter all over. So definitely the melting is not going on in the plagioclase peridotite stability field. It's going on in some other field. And then what you can do is simply ask, can we find a melting model which will actually fit all the observations? So what you do is then ask it to produce a slope of 1. And here is such. Here's various ones. This is from all the isotopes, different isotopes. And this is how well that model fits things which were not used in the inversion. And you can see that with the exception of strontium and lead, I'm not going to talk about separately, the fit is really excellent. Here are different ones. This is using just the lead isotopes, and this is just neodymium and hafnium. And as you'll see in a minute, they all produce essentially the same behavior. And here then is the result of doing all that, right, compared with the observations. This is the melting model got from Thessaloniki, compared with the observed concentrations from Sweco seamount. And you can see the fit. It's not, it looks as if it's a fudge, but it isn't. Right? I just went through my file of ocean islands to find out one which actually fitted well. And Sweco also fits this. Here's the evolution in 2 gigayears. It has one interesting feature from the, this is simply a comparison of the melting from all these different isotopic things, and you can see they're all very similar, and they're quite different from the Morb melting, the adiabatic decompression melting, isentropic decompression melting, which makes Morb. The melting distribution is quite different, as indeed it is beneath somewhere like Hawaii. This shows something which is going to be very important, I think, in the future. This is the same thing done from some melt inclusion data which John McClellan produced from essentially Thessaloniki. And that's this line here. And what you can see is that from melt inclusions from a really small sample measured with an ion probe using lead as the lead isotopes as the isotopic thing, that gives you a melting behavior which is really very similar to the others. So instead of having to map a whole region, right, which is how we started in Thessaloniki, you can just take a hand sample and do it on one hand sample, right? And it's provided you've got access to a good ion probe. So you need a budget of whatever, $2.5 million. I don't know what it is nowadays. It's around about that. And then you can play this game just on hand samples. You don't need to know anything about how to map lava flows in the field. Right? And that will certainly have an impact on the geochemistry. The other thing about Sweco is the bathymetry. The bathymetry is well known because this is one of the seamounts on which the Americans conceal their intercontinental ballistic missile submarines. So it's rather well mapped. And it's got a flat top. Right? It's what's called a geo. Right? And the flat top, presumably, like all of the geos in the Pacific, was formed by erosion, and that accounts for something which was very puzzling, which is why the oxygen isotopes don't correlate with any of the other isotopic systems. And that presumably is because this was originally above sea level, and the water fell on it and changed the oxygen isotopic ratios in the seamount. So, where else can we play this game? Well, we can go do this now quite extensively. I'm going to go through these sequentially. talk first of all about the Reykjanes, then about the Western Rift Zone and the Northern Rift Zone. The Reykjanes Peninsula, right, this Kornieff's work here, right, showed no sensible pattern whatsoever. On the other hand, John McClelland's work with with the iron probe on one particular volcano is absolutely fine. Now this is, I think, going to be a general problem, which is that if you take a large region, let me go back and show you the region. If you take a region this size, right, you're now going to sample quite a lot of different things coming out. And they come from different source regions. The mantle is very anisotropic, very heterogeneous. Right. And so when you put it all together, which is what I've done here, you get no sense at all. Whereas if you just look at one particular hand sample and do the melt inclusions in the olivines, it works fine. And the resulting model here is the melting model now compared with the data from Réunion, another ocean island, works fine. So Reykjanes Peninsula actually looks rather similar to Thessaloniki. It's right on the edge of the plume, and what we're seeing there is an ocean island basalt. If we move further east, or northeast to the Western Rift Zone, now we can do it actually with the samples. If I go back and look at it, samples are quite distributed, but it seems as if in that region anyway, it's not that inhomogeneous, so you could do the same thing, do the same comparison, right, with that one was with, this is with hafnium isotopes, right, this is with neodymium isotopes. We give essentially the same answer. Here's with the neodymium, here's with the hafnium. This is compared in this case with the Réunion, and this one with another island. Name I don't know how to pronounce, but you can see that they are actually both fitting with the same thing. Lastly, let me look at the Northern Rift Zone. Right. Here's the Northern Rift Zone, and now the situation is rather different. You can get a slope of 1, right? But what you now need is this now fits with morb melting. This looks like a morb. The source is with morb melting. So we can actually see over Iceland the whole. This is the comparison, right? This is Srico in the north. These two also. Réunion fits the melt inclusion data. Melt inclusion down from here, right, matches Réunion, as does the Western Rift. But the one in the middle, right here, Northern Rift, the best fit to that is morb. So it's not, I think, very surprising that what we're seeing is the subduction of seamounts. After all, they're the biggest source of fractionated material which is recycled into the mantle. And they seem to have, I mean, they're quite variable, their isotopic ratio is quite variable, as you saw at the beginning, and they seem to go down. The really surprising thing to me was that as a result, when you do this, when you play this game, you fit all the elements, right, that you measure. So the amount of what I was expecting, that when things get subducted, you certainly lose water from the subducting plate, but I thought that would bring would remove quite a lot of other elements. It doesn't seem to. And this also seems now to be the pattern if you look rather carefully at the basalts, for instance in northern Honshu, they show the same pattern, that they look like island basalts which have been melted by the addition of water. Right? So I now have doubts about our understanding of not for the first time, our understanding of what happens in subduction zones. I think that less happens there than I or anyone else had expected. The question, which is completely unsolved by all this, is what is the process which allows you to extract from, in the case of Thessaloniki up here, a column which is about 100 kilometers, all partially molten. The signatures are coming largely from the lower part of that column. How in the world does the melt, first of all, separate in this way and then move up through this column, right, without interacting with all that partial melt on the way through? And that seems to me one of the really major problems that any physical model of this process has got to solve. The other one, I'll say a little bit about now, which is not really new, is the question as to, first of all, how much melt is needed before you get separation, and how quickly does it reach the surface. And this really depends, both of those questions, that both of those issues depend on the uranium series isotopic scheme. And this just shows what happens, right, when uranium-238 decays, goes through a whole chain of different isotopes. And the reason why this whole chain is so useful to us is that the ratios of the concentrations of these different isotopes when you're in radioactive equilibrium is simply dependent on their half-lives and not on anything else. Right? And the reason for that is that obviously in equilibrium each of these steps must happen equally often. Right? And that is wonderful because it means that we know the concentration ratios of these isotopes right, in the source region, and these are all, right, the whole lot of them, because they have large ions, they're all incompatible. So these are the elements which we don't have really very good control on what the concentration is in the source region because it's so variable. But we don't need to worry about that. The mantle is certainly older, right, than 0.2 million years, and so we would expect the mantle source regions to be in isotopic equilibrium. And that's one of the ones we can use. The other one we can use is the decay series from uranium-235, and that goes through 231 protactinium, which is this one here, which then decays to 227 actinium. Now, in both of these, I've drawn a horizontal line across it. Let me go back to this one, across here, and that is because radon is a gas, and these things can degas, and that can mess you up no end unless you're clear about it, because what happens, right, if they degas is that you lose this one. So then if you're trying to compare the concentrations of ones up here with ones down below, you've got to worry about whether you've lost gas on the way through. And the solution to that is to have nothing to do with the ones down here unless you're interested in degassing. If you're interested in degassing, the one to go for is lead-210 with a half-life of 20 years, and compare it then with the concentration of radium, whose half-life is 1600 years. But I'm not interested in degassing, apart from it being a nuisance. The degassing, I'll just say a little bit about degassing. If you stop the supply of things above a particular level, right, and then let the isotope decay, it obviously decays like that. If you then start the resupply after a time delta t, then it recovers again. The rather strange thing about the whole of this business is that the recovery time for a particular isotope is governed by its half-life and not the half-life of the thing which is supplying it. And this seems really quite strange and just shows how little intuition one's got even about the simple solutions of a linear, ordinary, first-order differential equation. It's quite easy to prove, but it is, I think, surprising. If you then make everything dimensionless using the half-life of the isotope you're concerned with, C2, then you get this expression, and I'll just show you what it looks like. This is simply the dimensionless time for which you've interrupted the supply. And why it's important is that to make much difference to lead-210, you've got to interrupt the supply, right, of lead-210 for quite some time, like 2 dimensionless times. So it's no good just simply degassing the basalt as it comes out. That doesn't have any effect. You've got to degas it over quite a long period of time. And that really means that you've got to be losing carbon dioxide, which is that's the thing which bubbles out first, and that takes the radon with it. So looking at the lead-210 tells you what's really happening, right, to the carbon dioxide. So I'm not going to have anything to do with that. Now, the other thing which is useful is that here they are in equilibrium, right, and you've got some melt present. If you extract the melt, because both of these elements are incompatible in the solid, with thorium being more incompatible than uranium, then what happens is that you're left with a source region where this ratio, and generally we work in terms of activity ratios, which is the concentration times the decay constant, and that should be 1, right, because that's the thing which governs the stepping down the thing. When you extract more thorium than uranium, this goes to less than 1, and in the melt it goes to greater than 1. Then, if you leave it for some time, first of all, because of the half-life of the radium being 1600 years, this ratio goes to 1 first, and as it does in the source, and then finally, after quite some time, and the half-life of thorium is about 75,000 years, after that sort of time, it goes back to 1 in both. So, if you measure this ratio, you can tell how long it is since the material was in actual geochemical equilibrium with its source. And the result of doing that depends then on whether you let the thing regenerate. If you suddenly extract all the melt, then you end up, everything essentially, right, if you extract too quickly, you don't have time for the ingrowth to occur, and that you can also tell. So you've got also information about how quickly you are actually extracting stuff from its source region. So here's these are half-lives. Here is thorium-230, and thorium-230 with a half-life of something like 75,000 years is on the verge, right, of not having time to recover between extraction. Radium-226, no problem with. And the question then comes, these are the ones which you can use, which are above radon. So these are not affected by degassing. And the method you use to measure these, you can do up to radium by mass spectrometry. These ones you have to count alpha particles, and that's not as accurate as using mass spectrometry. We know, and there are lots of publications showing that things as far as radium, right, in young basalts are out of equilibrium. So we know that the time scale for the extraction from the source regions to the surface is less than about 1500 years. The geochemists say that no, that it has to be, all you can do is say it's less than 5 half-lives. Well, I'll show you in a minute that that's most improbable, because particularly with protactinium-231, the disequilibrium is about 2. So if you say, right, you've got 5 half-lives, then you've got to make an initial disequilibrium of 64. And nobody's ever seen anything like that. Right? It goes up to 3. So I believe that these estimates, right, are that the half-life is about as much as you can manage. The most interesting one is actinium-227, which is an awkward one to measure because it's actually, there isn't much of it. It's produced by the decay of protactinium, right, by alpha decay. And Ken Sims has been looking to see whether he can find any basalts in which this is out of equilibrium. And he's found one, and I'm not allowed to tell you where it is, right? But what that means is that the time scale for the transport, this stuff has to be less than 20 years. So I think the transport times are really fast. This is one of these complicated pictures showing the correlations. Really all that matters here is that here's 230, uranium-238, that's an activity ratio, and that's 1.3. Protactinium is bigger, it's 2. And this is very striking because geochemists regard uranium as a thoroughly incompatible element. Well, in order to get these fractionations, the melt fractions present, which are being extracted, have to be really small to fractionate it from 231 protactinium. Less than about 0.1%. So that's really the conclusion, and this is where I will stop. Can't make it from Morb. At least as melting begins, the residue melt fraction left in the source is no greater than a few tenths of a percent, and melt moves from being chemical equilibrium to its source, certainly in times of less than about 1,000 years, and probably in some cases at least less than 10 years. Now, finally, let me just say a word or two about essentially the nature of where I think one can go. I think there's a great deal more along the lines of which I've just talked, right, of looking at the geochemical consequences of the geochemical implications of all these melting models. The geochemical technology is moving faster than any technology I've ever had to do with up until now. Right? The costs are going up. Right? The instruments are getting very much more expensive. But the end of that process is not in sight. The geochemists go to enormous trouble in clean rooms to separate the things they want to measure. And then their instruments throw away between 99.9 and 99.99% of what they've separated. So the opportunities for improving the instruments seem to me just enormous. Right? If you could do it, if you could only throw away, let's say, 70% of what you separated, that would have an enormous impact on what you could do. And that is perfectly on, right? It's a difficult thing to do. Various people, Grenville Turner's done it with xenon. You can do it, but it's really difficult, and at the moment you have to be essentially a card-carrying physicist to design an instrument which will do it. But that will change. Now, so I expect them to make an enormous number of more measurements, of much more higher precision on the smaller samples, and that surely, just like with the ion probe, that will change things. And the ion probe's already available. One can do an enormous amount with ion probery. The ticket is only 2.5 million, and lots of universities can afford that sort of price, right? Even if the granting agencies can't. The other side of this is really the experimental side, and the general feeling is to work with silicates and try and extract melts from silicates. Now this requires a very special technology to work at very high temperatures, right, under controlled atmospheres, and it's really very difficult. But Yasuko Tokai has been working with a material called borneol, right, which is an alcohol, though you wouldn't guess it from its behavior, right? And this you can work with at room temperature. The only problem is it evaporates, so you've got to actually protect it with things like cling wrap from evaporating. But cling wrap is very cheap compared with any of the things that the proper material scientists use. And what we really want to know is what is the process which produces the channels which allows these melts to move up so quickly. Now, the work that has been done, that experimental work, has been done at rather high stresses. And I think the stresses involved in, for instance, Silica in the melting zone are much less than that. And something, right, allows the channels to form. The channels don't need to be very big, even if the 10-year timescale is correct. And the assumption that we've all been making is that we can use continuum mechanics to understand what's going on. Well, the channels don't need to be much bigger than a grain. And it's not clear to me that you can safely use continuum mechanics to understand this process. And there's not been much work done on the behavior of aggregates of crystals, right, when they are undergoing essentially diffusion creep under small stresses. And I would like to see that done both in the laboratory and also done with mathematically. I had a graduate student who started this, but sadly he dropped out and he never wrote up. But it's perfectly tractable to attack this problem, right, with using essentially ideas of diffusion creep to see what will happen, right, when you take a material where you're actually worried about what happens on the grain scale. And those seem to me the two areas in which real progress can be expected. But old men like me are not good at predicting where things are going to go, and I will be totally unsurprised if what I say in a few years' time looks stupid. Right. I hope it won't look stupid. It may be wrong, but I just like dislike doing things which are wrong because they're stupid, rather than wrong because I didn't actually understand the physics. And with there I'll stop. Thank you.
Thank you very much indeed, Dan. I'm sure we have some questions.
Everybody believes everything.
Everyone believes absolutely.
I can't believe
Come on,
it.
Rich, go on then.
Okay, so it's more of a technical question, but for my benefit, and I think for a lot of people's benefit, when you show those rare earth element inversions, what are the variables that you're inverting for? Can you say a little bit more detail about that inversion?
I'm inverting simply for the melting distribution on the assumption that it only increases as you come closer to the surface. So I impose, you don't have to, you can change a flag and it doesn't do that, but the one that I showed you requires that the melt to increase coming towards the surface. And then it just simply, inversion is slightly the wrong word. I mean, it's just brute force. You just do lots of forward problems, see which fits, use a simple-minded thing to improve it. I use Powell's algorithm to find a solution that fits. Now, in terms of what controls it, the major control on those melting curves is essentially the difference in behavior it's controlled essentially by what the aluminium is doing. If the aluminium is in garnet, that has a very strong, I mean it makes the heavy rare earths are really strongly retained by the garnet, and the light rare earths are incompatible. Right. Once the garnet disappears, the behavior is controlled by CPX, and that has a rather different distribution, which is that the middle rare earths right, and the heavier rare earths are pretty much the same. So really it's looking at that behavior. When the melting is as big as what I showed, right, it's essentially a dilution effect. Right, the inversion has to produce a particular amount of melt just to dilute them to the concentrations you see. In terms of what you can get out of this, what you get really is the total amount of melt and where it begins. Right, those are the two variables, and that pretty much is all you can get from measuring the concentrations of all the elements in the periodic table. Right, they all look as if at the moment, with the accuracy of the partition coefficients we've got at the moment, that's really all you can do.
Can I just how much does the result depend on your assumptions about the trace element concentrations in the source material, and B, about the sort of combination of lithologies, whether you have garnet peroxenite versus Hartsbergite in the source, or Lurzelite?
Makes a tremendous difference. Right. The reason why I showed what I did was that one of our major constraints on the source composition is whether we can actually generate the right composition for 7 kilometers of melt, because that's the process of melting under ridges is one of the best averaging processes we've got, right? And so you've got to fit that, and that was really the point of what I did with Bob, right, and Keith. It makes a difference to the volume. The point is that the concentrations vary by 2 or 3 orders of magnitude, right? And all those plots I showed you are log plots, and so it isn't terribly, the actual result isn't terribly sensitive to what you choose for any of these things, right? But the real result is because of the enormous variation in the amount of melt you extract. Right? And I don't think, the geochemical, the chondritic uniform reservoir, I think, is really quite a good start. Bob has something to say.
Yes,
yeah.
Bob does. Yeah.
Yes, you made the case that you melt at tiny percentages of melt and they start to move. Is it your view that 100%...
They extract.
Sorry?
They have to extract.
You have to extract. So just to clarify this, is it your view that 100% of that melt, which starts at very low fractions, is extracted from the mantle? You're leaving nothing behind?
Nothing is too strong a word.
Well, how much might you leave behind?
If you look at if you believe the compaction equations, you can extract down to about 0.1% at these low viscosities. The initial melting takes with it all the water and carbonate, and that both of those things lower the viscosity, and that means that the melt fraction that you extract later on, once your big major silicate melting starts, may be a little bit higher. It may be several tenths of percent rather than less than a tenth of a percent. But I don't think you leave behind more than a few tenths of a percent, no.
Oh.
So speaking of major silicate melting, your model for the source of, let's say, Theistereker is melting of a subducted seamount basalt. That's the entire source. There's no matrix, there's no peridotite, there's no depleted component.
No, that's not correct.
So
no, that's not right. All I'm seeing is the incompatible elements. I'm quite sure from its composition that it equilibrates with some sort of background peridotite. Now, the question which I would love to know the answer to is, clearly if you're subducting oceanic lithosphere, down goes 7 kilometers of oceanic crust. That then, if these various calculations are right, is scarcely changed by going through the subduction zone. So something like 7% of the mantle must be subducted to oceanic crust. And what does it look like why do we see so little signs of that in what comes out? Right? I mean, one of the problems is that it doesn't fractionate the incompatible elements. Whether you're going to see it in the major elements, I simply don't know. That's going to be a question of reaction times, because it's got actually to come through, right? You know, you've got 100 kilometers of partially molten stuff at high temperature, and it's got to come through all that. So what reactions do you get on the way through? Don't know. Right? Would love to know. Well, I would love to have just one borehole which went through a piece of the convecting upper mantle. Right? The best we can do is look at places where the spreading rate is so slow that it does not produce much melting. Southwest Indian Ridge, the Gakor Ridge, places like that. But the problem with that is that it's so tectonized. I really think we're going to have trouble in reconstructing what it looked like before it got involved in the upwelling.
Yeah, I have a question about your last comment in the presentation. You said that we need new mechanism for channel formation. Why are you unhappy with existing mechanisms like porosity waves or like porosity waves or reaction and filtration?
Oh, porosity waves are too slow. Right, even at 25% melt, they can't do it. Right. Certainly, reaction and filtration can do it, but it can't start that way because it won't react. After all, it's being produced from a source region, and we've got to get channels right from the word go because of the timescales. So something does it. I don't know what does it, but I don't think any of our existing methods will actually produce channels fast enough. I think it's some sort of instability, and it's some sort of instability which is produced by the melt being there.
Paul? Okay.
How short a time scale do you have to see before you stop believing that it's coming from the melting region rather than being generated in the crust or due to some unmodeled fractionation process?
Well, but the trouble with fractionating it is that all these things are so incompatible, right? So it's extraordinarily difficult. I mean, you can play all kinds of games. Right? Radium, for instance, people play games with, right? Protactinium, that starts to get... Now, that's the biggest of these disequilibriums with protactinium. That's even harder. So I mean, yeah, they're all showing the same thing. When the first one was discovered, 230 thorium, people came up with all kinds of special pleading, right? And this special pleading has got less and less as more and more of these anomalies have been found, right? And I think I keep on bullying Ken Sims to publish, right, this stuff, and I think that will stop even more of it. I think it's very hard. I mean, I'm a simple-minded scientist, right? This, I mean, I know well, I think I know that you can have melt separation down to 0.01%. That accounts for everything, provided I can get the stuff through. And we've got to keep this huge variation right up to where these melt inclusions form, right? And they form in Thessaloniki, not in the crust, but in the upper mantle. So you're rather stuck, right, for all the various things of people wanting feldspar and stuff. Hard, because these things are, you know, they're fractionating only a few percent, right, to make these melt inclusions. And as John McClellan has shown, everybody's called John, as John McClellan has shown, once you start to fractionate in the magma chamber, right, then the whole of the heterogeneity disappears. Right. So really what we're looking at is right back to the early, to the stuff, which has undergone really very little mixing, even by the time it mixed to these magma chambers. Coffee.
Okay, yes, you're right there. So yes, we have a coffee break now. So we start again at 11:30 with Paul.